Alright, there. Alright, good day. Welcome back. Last time I promised you, um, that we will deal with Le Chatelier's principle. Um, I think it's preferable that we move to acids. Then I'll make a separate video on Le Chatelier's principle because it's short. Um, let me deal with the longest chapters first, right? Now, today we'll be speaking about something that we are familiar with. Let us speak about acids and bases, right? I'm saying we are familiar with this because this is a common concept. We have an idea of what a base is and what an acid is, normally because we are common with batteries, and we know that most batteries consist of acids, right? Especially car batteries, right? We know that they consist of acid. So again, we know that um, vinegar, we are familiar with vinegar, right? And vinegar happens to be a base, right? Now, it's nothing. Let us get into the topic. Uh, yeah, let's see. We have acids and bases, right? Many substances that we encounter in our daily life can be classified as either acids or bases. For example, aspirin, right? It consists acetyl salicylic acid, right? Um, milk of magnesia um, is magnesium hydroxide, right? Which is approximately a base, right? Now, we also have, right, in the previous grades, we regarded acids as substances that ionize to produce the hydrogen ions, right? The plus ions, right? And bases, this ones we said they completely ionize, right? They ionize to this form, right? Now with bases, these substances, they ionize to produce what? The OH group, right? Um, we have many definitions for acids and bases. That one we know, so we're not gonna deal much on it. Uh, let us just talk about these. Let's get into the properties and whatnot, right? Now we have the properties of acids, right? Properties. Um, we have acids and we have bases, right? I'm going to try to make them simple, right? What are the main properties of acids and what are the main properties of bases, right? The first thing is acids are sour, right? Yeah, acids are sour. Acids are sour. Now remember, when I started the video, I said vinegar is an acid, right? I said vinegar is a base, but according to this statement, we're saying acids are sour and vinegar is sour, which means if we were to give example, the first example would actually be vinegar, right? It's sour. Another example might be acetic acid, right? Acetic acid. Another example might be what? Another example might be citric acid, right? This is found in citrus food, the citric acid, right? So vinegars are acids, not bases, because they are sour. They have a sour taste. Number two, acids cause specific color changes, right? They cause specific color changes in indicators and plant. Yeah, they have a specific color changes, right? Specific so yeah, specific color changes. Color changes, right? Number one. Okay, this side. Let's go to number three. Let's go to number three. Now, we're not done with acids, right? Number three, we can say aqueous acid solutions conduct electricity, right? Aqueous solution acids conduct electricity. Acid solution conduct electricity. All right. Let me cancel this, right? Conduct electricity, right? Now number four, what are the acids can neutralize bases, right? Acids can neutralize bases. Acids neutralize bases. Number five, a substance that has at least one hydrogen that can ionize to form them in aqueous solution. As long as it can ionize to form this, then it's a base, right? Now let's go to the first one. I mean, it's an acid. Now when we talk of acids, they are bitter. They have bitter taste, right? Example might be soap, right? I might just give you an example with soap, right? Number two, what are bases? Bases, they also form specific color changes in indicators, right? This is their similarity. They form specific color, specific color changes, right? Number three, what do they say? Obviously, if acids can can conduct electricity, we go on to say they can also alkalines, right, which means bases, right, can do what? As alkaline solution conducts electricity, right? That's what we can say about it. Let me do it like this. Can conduct electricity. Now, number 4. Number 4. We said what? Bases neutralizes acids. Obviously, the opposite of this, right? Bases neutralizes acids. Now, number 5. Obviously, in a reaction, if we have an outcome of the OH group, the hydroxyl group, right, that is a base, right? It produces the hydroxides in aqueous solution, AQ, right? This one also in aqueous solution. Now, these are the properties that we are familiar with, right? It's nothing new to us. Now we have acids and bases. We are going to talk of them in terms of the Arrhenius and the Bohr and the other model, right? Let's start first with the models, the acid base models, right? What are acid base models? Then from there we will dive into it, right? Now we have acid base models, right? Now let us look into this. In the late 19th century, the Swedish chemist Svante Arrhenius, right, formulated a definition for acid and base, right? And in terms of an acid, the Arrhenius representation in terms of acid, Arrhenius representation in terms of acid, number 1, in terms of acid, we say an acid is a substance that ionizes in water to produce what? It ionizes in water, ionizes in water to produce what? The hydrogen ion group. Now the base, it ionizes in water to produce, it produces the OH group, right? Now that is in terms of Arrhenius. Now we also have another one we call Bromstead-Lery, right? Now remember, these definitions here are in terms of aqueous solution only, right? Now, which meant it wasn't sufficient, they weren't necessarily sufficient definitions. So there came this other man called Bromstead-Lery. So we're just gonna say Johnston Bronsted, right? So I'll just write Bronsted, right, like that. This is Bronsted definition in terms of acids. Then Bronsted says acids are proton donors. Acids are proton donors. Are proton donors, right? Now bases are proton acceptors. Proton acceptors, right? That is in terms of Bronsted, right? This means that H plus, they donated this, right? This means that this received this, according to Bronsted. According to Arrhenius, this ionizes completely and this is produced, right? Now, that's not so bad. It's good. No harm done. So, we can look at it in terms of a reaction and see who was right, or who we can agree with, right? Um, when hydrogen chloride gas dissolves in water, hydrochloric acid forms, right? If I try HCl plus H2O, right? Um, and this is most likely to form what? H3 plus, right? Chlorine plus chlorine here, plus chlorine. Now, all of these are in aqueous solution, right? This is in aqueous solution. This is in aqueous solution. Now, this is in aqueous solution. Now, this is in gas form. Remember, hydrochloric acid is a gas and this is a liquid. Now, that's good. We have a gas and a liquid. It forms the aqueous, right? Now, that's good. Let's look at it in this way. Bronsted said an acid is a proton donor. This is an acid. It's a proton donor. Now this will serve as a base, right? Remember that water is an ampholyte. An ampholyte simply means that it can serve as a what? As an acid or as a base, right? Now that's basically what an ampholyte is. Then water in this case will serve as a base. Now, what is going to be formed is going to be what? This is going to be the base, the conjugate base, right? And this is going to be the what? The conjugate acid, right? This is going to be our conjugate acid. I'll tell you in a bit why I say it's going to be that, right? Remember we said, according to Bronsted, a base is a proton acceptor. Water accepted what? It accepted the another hydrogen from the hydrochloric acid. That's why we have H3 plus, right? Now, again, chlorine is left alone there. It's an acid, right? So we call it the conjugate acid. So if we were to come and if we were told to put them in conjugate form, this was to go with this and this one was to go with that one, right? With this one, this was the conjugate as the conjugate base, and this will be the base, and this will be the conjugate base, conjugate acid, and the acid, right? Now we'll come to that. So basically, this is what he meant. Arrhenius principle. This is not so. Bronsted. This is not so different from Arrhenius, because Arrhenius says it ionizes in water to form the H plus, right? Meaning that if we look at this thing has ionized and it donated hydrogen to this form, forming a hydrogen plus, right? Meaning that this is an acid, right? Correct? Good. Now also, if we look at the definition of the base form, we say it produces an extra OH, right? But in this case, we see that we have a what? A positive H, right? Then it alters the meaning in terms of the base, because what he specified only focusing on aqueous solution. So now we have a gas here, we have a liquid here, which changes his statement a whole completely, right? Now that's good. um that is in terms of Bronsted Lorry, right? Yeah, that's what we need to understand, that bases are the proton acceptors, right? And acids are the proton donors, and also that acids, they ionizes to form a H plus, right? And the basis ionizes to form the OH minus, right? Now we will investigate the Bronsted in terms of aqueous solution a little bit later. Once we get to this, uh, reaction equations of aqueous solution, right? The reaction equations of aqueous solution, of aqueous solution. This is basically uh, reaction, right? And this is what equation, right? In terms of aqueous solutions, right? Let's say we have the same reaction, hydrochloric acid plus H2O, then it again forms the H3O plus, right? Plus what? Chlorine, like that. This is in aqueous form, right? This is in aqueous form, this is in aqueous form, this is a liquid, and this is a gas, yes. Now we want to investigate this. Remember, this is a proton donor and this is a proton acceptor. Now these reactions, acids and many bases, dissolve in water to form aqueous or watery solutions. When we say aqueous, we mean watery, right? Now we can give an example of this. A gas plus a liquid gives water. The solution, the products which are in watery form, right? Now we can also give another example in terms of the HNO 3, right? Which is a gas, right? Which is a gas plus the what? The H2O, which is a liquid. Obviously it will form a what? A similar reaction as the other one, H3O plus, which is going to be in aqueous form, right? Plus what? NO3 negative, right? Now all of this is just a simple explanation to say gas plus liquid likely to form an aqueous solution, right? Or an aqueous product, right? Whatever you're going to add, right? If you have a gas and a liquid, most likely you will get an aqueous solution as a product. Now we can get some solids to be in that form. For example, the H4SO SO4, right? Sulfuric acid, which is a liquid. I mean, which is, yeah, it's a liquid, right? Sulfuric acid, and what? And water, right? They form what? They form H3O plus, okay, plus what? SO4 minus 2, like that. Now it's not so bad, right? It's not so bad. This is the acid, hydrochloric acid, right? This is water, right? This is in liquid form, this is in liquid form, and this is in aqueous, and this is in aqueous. Per se, if you lose this a hydrogen from this side, know that your solution will end up being in aqueous form, right? Now, if we want to balance this, we're going to put 2 here, right? Now, also, we're going to put 2 here. Now, the equation is balanced. Now, that's basically almost all I can talk about at this moment in terms of in terms of acids and bases, right? We have the conjugate pairs, we have the conjugate acids, right? Now, remember the last time I spoke about conjugate acid and conjugate bases, right? Um, what I did not tell you is that when we say it's a conjugate acid or is a conjugate base, they do not necessarily correspond, right? What do we mean by that? If this is an acid, right, and this is a base, and this becomes a base, and this becomes an acid, right? It changes the complexion of the entire thing, right? We have an acid, a base, and an acid. Now, listen to me. Um, this and this are the conjugate pairs, right? And this are the conjugate pairs, right? This is acid, is known as the acid to base pairs, right? Acid to base pairs. Now this is also known as as a base to acid pair, right? Now this is known as a conjugate pair in simple terms. We call this a what? A conjugate pair. So you need to understand that there's a base, there's an acid, there's a base, and there's an acid. Identify them and know that they are conjugate pairs, right? Now, these pairs, in simple terms, we call them acid to base pairs, right? The acid to base pairs are conjugate pairs. Now, I told you about an ampholyte. We spoke of water as an ampholyte. We said ampholyte is a substance that can act as a water. As a base and as an acid, right? Now we also have what we call salt hydrolysis. Now, salt hydrolysis. Hydrolysis means the breaking down in terms of water, right? Now, salt hydrolysis is when acids and bases react with each other and they form a salt and usually a water, right? Acid plus base, they form a salt and usually a water. It's not always the case, but in most cases they form a water, right? Something like this, right? Any reaction whereby a salt and a water is formed is known as a hydrolysis, salt hydrolysis, right? Now, that is good. This reaction can also be called neutralization reaction, right? Neutralization reaction. Remember, we have a pH scale, right? A pH scale is used to measure the strength of a base or an acid, right? So on the pH scale, we have what? 1 up to what? Up to 12. And we agree that at 7, this is going to be what? Actually, I think it has to start from 0 here, right? This 7 here that we see is our neutral form, right? This is a strong base and this is a strong acid. Now, neutralization or neutral solution is in this form. We mean that the pH of that is going to be at 7. Then we'll deal with that when we deal with calculation. We also have an alkaline solution. What is an alkaline solution? An alkaline solution, these are salts that are derived from a reaction between strong base and a weak acid, right? Strong base, let me rewrite this, right? Strong base plus weak acid hydrolyzed to form a what? To form an alkaline solution. Remember, bases are also known as alkalis, right? So yeah, a strong base and a weak hydrolysis to form an alkaline solution, right? Now we can give an example of this one: sodium carbonate, CO3, which is a solid, plus water, H2O, which is a liquid. It can react to form 2Na plus, which is in aqueous, right? Plus CO3 minus 2, or 2 minus, sorry, it should be 2 minus, it should be 2 minus, right? Which is also in aqueous solution. This is an example. This is an alkaline, right? This is a base, this is a base. This here is an acid, this here is a base, right? This here is an acid, right? This will serve as an acid. Then being an acid, it forms an alkaline solution. This is a solution, right? Sodium is an alkali. The carbonate is an alkaline solution as well. Now, this is practically what we talk about when we speak in terms of the alkaline. We have also the acidic solution. An acid, another name for an acid in it's known as an acere, right? Acere, right? An acid. So this basically, we can say, salts that form after neutralization between strong acid and a weak base, right? Now, all of this, when they hydrolyze in water, they form acidic solution, right? A strong salt, a salt that is formed after the neutralization of a strong acid and a weak base. When a strong acid react with a weak base, strong acid plus weak base, they form what? They form what? They form salts, right? That is what you need to really understand about this topic. So basically this is what I wanted you to know, right? Then let me just show you this last part here, then I wrap up everything. We have what? NH4 Cl, right, plus what? H2O, right? This forms what? NH4 plus, which is in aqueous, right? Then plus what? Cl negative. Then this is in aqueous as well, right? This is a solid. This is a solid here, and this is a liquid, right? This is supposed to be your salt, right? Ammonium chloride, right? But now it's not going to serve as a salt, right? This is supposed to be your salt, ammonium chloride, right? Now it can ionize in water to form ammonia plus chlorine, right? Now that is basically what we talk about when we speak of an acidic solution, right? The hydronium ions will give an acidic solution, which means it's going to be less than 7. That is what I wanted us we talk about for today. Then next time I'll continue on reactions of acids and bases. Thank you.